Alright guys, so to finish this series up, I promised y'all that I would go back over all this stuff and explain it step by step. It's a lot of stuff to go back over, but I am going to do just that. So, first off, we did a lot of stuff in this, and it took a lot of stuff. So, what we did is we created a blueprint interface so that we could communicate without having to do a direct cast or a specific cast to our character inside the animation blueprint. We set up some values as outputs that we were to pass to the third person NMBP, and we were getting those right here by getting a general character reference, which is the parent class. If you look up here, parent class character, it's the parent class of all character classes, or all characters, I should say. So that's how we're getting the values. Inside of here, we are we're setting a reference on begin play. We did that on a begin play graph, which is kind of pointless for our scenario, but I did it anyway just for brevity, because that's how they do it. So under tick event, we're first setting the essential values, so we're calculating the essential values, we're updating our grounded rotation, and based on rotation curves, and we're catching values so that next time we can calculate the values correctly. So one of our catched values was our yaw, so we save the yaw after we've set the essential, after we've used it in calculations over here. So previous yaw is just the view rotation of our camera along the z-axis, and right here we're getting the current control rotation, and we're subtracting the last rotation from it. We're dividing it by the world delta seconds to give us the amount of rotation, or it's given us a value that represents the rate at which we're rotating the camera. Over here we're getting the velocity, we're getting the vector length, and we're using that as the speed, because when you get the vector length, it gets, think of a vector not just as x, y, and z, but as a line that's being drawn from one point to another point, and that's how you can look at it as a vector. So when you want to know what the general speed of this general speed is, you can get the velocity vector and you can get its length. So that's how you do that. We're doing something similar for the has movement input right here. They use this for other things as well, not just for calculating the has movement input, but also the acceleration. So we're getting the current acceleration, we're getting the vector length of that, and we're dividing it by the max acceleration. So getting the vector length gives us the value, which represents how much acceleration we currently have, with disregard for the direction that acceleration is moving in, and we're dividing the max acceleration, and that's giving us a kind of like a normalized value that represents our acceleration. So if our acceleration is greater than 0, then we have movement input. So moving on, this is get essential values, our interface right here, our blueprint interface, where every time that the animation blueprint is updated, it calls this update character info, which calls our blueprint interface right here, and it sets these values that are being sent over from here. So when it calls it, this function gets these, it does all of this, and it returns it. right here, we're manually rotating our character rather than using root motion. And so on can update movement rotation, we're saying, let me actually go back in here. So is our speed greater than 1? And let's see. Yeah. So is our speed greater than 1? Is our do we have any acceleration? So if our speed is greater than 1 and we have any acceleration, or our speed is greater than 150, and so if either one of those are true and we don't have a root motion animation playing, and we do this check so that if later on we decide, hey, we want to play a root motion animation, okay, well this is going to make sure that can update movement rotation is false, so that it doesn't try to manually move or rotate the character during a root motion animation. And that's the reason why we're doing this part here. So moving on, after we've confirmed that can update movement rotation is false, then we're getting the rotation amount curve, which is being set and scaled inside of our third person NMBP. So if you remember, let's see, under one of these, so update, okay, it's TurnInPlace. Yeah, so TurnInPlace right here, we're scaling the rotation scale. So this gets scaled anyway. So if the absolute value of this is greater than, basically greater than 0, with a little bit of error correction there, then if that's true, then add world rotation, and we're just getting that curve value and we're multiplying it by the world delta seconds multiplied by 30, which is the same thing as saying world delta seconds divided by 1 over 30. And we're using that as our Z rotation, or our yaw. And this part right here is only so that we can make sure that this is frame rate independent. So if the character has like 30 frames per second, this will ensure that that we still get proper animation rotation. So we created a getAnimCurveValue function, which just basically gets the curve value and returns the value, or returns 0. So if it returns 0, obviously it's not going to rotate the character. So we've covered all of that. So let's come over here and cover this. Alright, so on initialize animation, we're just cast into a general character class. That's what we're using throughout here. We're using we're setting our delta time so that we can interpolate, or interp to, I should say. So we're updating our char info right here, updating our aiming value. There's only one calculation in here that we need to do, and that's get the angle between where we're looking and where the mesh, where our character is facing. So we're getting that angle. We're using the Z, which is this rotation, or the Y pitch, which would be kind of like side to side, I guess, right here. Anyway, so we're getting those two values, and we're using those later on for setting our we'll get to that. So right here we're doing update foot IK. We're setting our foot locking. These values are actually not initially set. They will be set by reference inside of here. So if you remembered, and I hope you didn't forget to do this, but you have to set these to pass by reference so that we can modify those by reference inside of our function. So we have an enable foot IK left curve, which is being modified on our animations. So our animations can have control over these so that we can turn foot locking or foot IK on and off, and foot locking on and off. And I do believe I remember going over that, but if not, I should probably just go ahead and go over it anyway. So if you see right here, so it's off, and then enable transition comes on when both feet are firmly planted on the ground and aren't going to move. So that's when he enables the transition to the next one. And if you watch the foot lock left, this is his left foot. As it comes up, he turns the foot locking off, and when it settles down, that's when it's completely off, and then he waits a few frames and then turns foot locking back on, and does the same thing for the right foot. So over here we're getting our foot IK curve, and this wasn't really, I don't think, really necessary for this because we didn't set up the foot IK. But anyway, I did another video on that, so if you want to look into that video, I would suggest you do that. So if the curve value is greater than 0, then we can do this stuff. So if it is, then we get the foot lock curve, and that's the curve that's being sent in here. So this right here, for example, for foot lock L, and we're storing that as a foot lock curve value right here because we're going to be using it. So if the foot lock curve value is greater than or equal to 0.99, so in other words, if foot locking is on, or if the foot lock curve value is less than the foot lock alpha, which in this case is actually not initially set, but the foot lock alpha gets set right here actually, and it gets set to the foot lock curve value. So if either one of these are true, if the foot lock is on or the foot lock curve value is less than the current foot lock alpha, then we will set the foot lock curve value as the foot lock alpha. And what that allows us to do is it allows us to initially bypass this on check and go ahead and set it anyway, and then yeah, so this is for our foot lock curve alpha. So if it's on or it's less than the current foot lock alpha, then we're going to set the foot lock curve value as the current foot lock alpha. So our foot lock curve value is our current foot lock curve value inside the animation. So if the foot lock curve value is less than the current foot lock alpha, this right here, then that means it needs to be changed to on or off, and that's what we'll do. So over here we're getting the foot lock alpha again, and we're saying, is this on? If it is on, then we need to set the current foot lock location to the socket transformer using RTS component space, and that's it's basically getting the location and rotation of our feet at that particular time in the animation. And all this stuff right here is doing is it's saying, is it's storing these values. That's all it's doing. It's storing values for our current foot location and rotation, so that it can pass it to this, and this is where it resets it back to its previous state. So if the foot lock is on, then we're going to pass in the current location and rotation, and inside here we're going to basically get the previous location and rotation, and we're going to set it back to those, we're going to set the location and rotation for each feet back to where it was. And that's when over here inside our foot IK animation layer, that's where those values get set. That's where it moves those bones back to where they were using the transform modify bone node. So the character is moving on the ground. We're going to get the actor's current rotation, and we're going to get the angle between that and the last update rotation, which comes off the character movement. That's going to be our rotation difference. Our location difference is going to be the velocity multiplied by world delta seconds. And what this is basically doing is it's getting the amount of velocity since the last frame. That's all it's doing. So the time between frames, this will be your velocity between frames. And we are going to unrotate that vector. And remember I told you, imagine a vector is a line pointing in a direction. And we're going to unrotate that with using the mesh's world rotation, so that this velocity vector will line up, always be aligned with the character's rotation. And that's going to be our location difference. And so we're setting our local location right here, which is our current foot lock location, which is being stored out here, which is actually going to either be our left foot location or our right foot location. And we're setting that to rotate the vector around an axis. So we're using -1 to kind of invert it along the z-axis. So this will rotate it in the opposite direction, rather than rotating it in the same direction that it's moving. We're going to rotate it back towards where it was the previous frame. So we're getting the local location, we're subtracting the difference from it, and that's our vector, and then we're just rotating that around the rotation difference. And that's essentially, it's just putting the foot back where it was. And we're doing the same thing with the rotation. So yeah, let me go ahead and do that actually. So this is where those values actually get set here. As you can see, we have our alpha as the alpha. We're using the transform modify bone. We are replacing actually the existing, and the reason why is because we want to put it back where it was. We don't want to add to its current placement or rotation rotation, we want to replace it. And I think I kind of already made this clear, but all they're doing is every frame they're just putting the foot back where it was. So every time the animation moves the foot forward, they're going to move it back where it was. And that's all they're doing. I don't think there's any better way to do that. If anybody knows, they might want to let them know, and let me know too while you're at it, because I'm assuming there's just no other way to do that. You would think there would be, but apparently there's not. So set foot locking for both feet. And let's see. So the should move check, it's basically what we've seen before. You know, if the speed is greater than 1 and the player has any kind of acceleration, or the speed is greater than 150. Now 150 is the walking speed of your character, of your ALS character, and that's why that number is 150. So right here we're just doing some basic logic here. I'm not going to go into this, I already kind of touched that. Can turn in place. In this case, we're not checking to see what rotation mode or view mode we're in, like they do, because we didn't need that. We just need to know, is enable transition on? Is it 1? You know, is it greater than 0.99? If so, then do a turn in place check. If not, reset our timer. So our turn in place check right here, we're just getting that that X angle, and if you remember over here in our update aiming, our X is our yaw. So if the absolute value of that is greater than an angle of 45 degrees, and the rate at which we're rotating our mouse is greater than 50, that means we're rotating quickly. Actually, I think that's supposed to be less than 50. I'm pretty sure that's supposed to be less than 50. In fact, let's double check that, because I think I might have messed that up. Because you want to make sure that they're not rotating quickly, because if they're rotating quickly, so if the rate at which they're rotating is high, that means they're rotating quickly rather than slowly. And so you only want it to move when that value is less than 50. So if that value is less than 50 and we've rotated more than 45 degrees to the left or right, then we're no longer looking forward. And if that's not the case, if we are looking forward-ish within a 90-degree angle, then we're going to reset our timer. If not, we're going to add to our timer. We're going to add the delta time to our timer. And over here, this just allows us to base the amount of time we have to wait for the character to rotate in that direction off of how far back we're looking. How far back do we need to rotate? So if we're looking directly behind the character, he's going to rotate quicker. But if you just look barely to the left, it's going to wait maybe a second or two, and then he'll rotate to the left. Whereas if you were looking right behind, it would be almost instant. And that's what we're doing here, and that's why we're using the angle, and we're saying if this is greater than that. So over here we're just using our aiming rotation Z axis for a turn in place. We're getting the angle between our camera angle and our actor's angle, or actor's rotation, and the camera rotation. That's going to be our turn angle. We're using that turn angle to say, hey, are we looking beyond, is our view within 130 degrees? You know, if If not, then we need to turn one. Then we're looking behind the character, and we need to turn 180 degrees around. If it is less than 130, then we only need to turn 90 degrees. Right here, we're just setting our values using a struct. Over here, we're just saying, we're just checking to make sure that this animation isn't already playing. If it's not already playing, then we play it as a dynamic animation montage. And if we have set these to scale turn angle, then we will scale it. If not, we're just going to use the play rate as the rotation scale. So if your play rate is 1 or greater, then you should probably have that. Is just solid 1, then you should probably have that turned off, so that the rotation scale is scaled up by 1. Basically that's saying that the rotation amount curve on your animation will be multiplied. The current value of that will be multiplied by 1. If not, then we're going to, if we do want to scale it, then we want to get the current turn angle, divide it by the amount or the angle at which we're turning. So negative 180, 180. We're dividing that by our turn angle, which is the angle between where we're looking and where the character is facing. And we're multiplying that by the play rate. And that's going to be our rotation scale. And then that rotation scale is in turn used to scale up stuff elsewhere. So we'll cover that here in a second. So we've covered that aspect of it, and there's just one more thing to do. So let's go over to the animation graph, and we will go in here, and right here we have our default state machine. And I didn't do anything with this. This is just the default one, default template. We got our location states right here. We're saying, hey, if it's not moving, get our pose and set our foot lock left, right, and enable transition. Then we can play whatever animation is. We can check to see if we need to play an animation on this slot. After that, we need to scale up our rotation amount curve on that animation, or the current rotation amount curve that's being stored. We need to scale that value up by this rotation scale, and we are scaling it. Under apply mode, we select scale. So to come out of that, we're just using a boolean. To come back, we're using a priority of 2 because we want to stop. We want to do the stop transition rather than going from moving to not moving. But there are cases where we still need to go from moving to not moving. So we have that set but as a priority 2, so it doesn't take precedence. And we have a quick stop transition that gets fired over here on our event graph if we do use that one. So that's over here. Now, under moving, we're just using our catch pose for locomotion cycles. So if you remember, that's this right here, our default locomotion cycle. So this is firing that. So over here, we're just saying we're making sure that we're fully blended before and we should move before we transition over to the stop state. Get out of the stop state. We make sure that we're fully transitioned to the stop state before we go from stop to not moving. So under our stop state, we got a pre-stop state here. That's a state. And off of that, we got two conduits, foot up and foot down. As our conduit rule, we're getting the feet position curve. We're getting the absolute value of that and making sure it's greater than or equal to 0.5. So if we come over here, let's see. So if I come over here to turn in place, I believe it's under locomotion. It's on our run and walk. So over here, you'll see that for the left foot, for the left foot, it's the value is negative 1 when it's pretty much on the ground or close to the ground. As the right foot comes forward, but it's hovering in the air, we set that to a positive 0.2 value. When the right foot is on the ground, it's a 1 value. When the left foot comes forward but it's off the ground, it's a negative 0.2 value. And when the left foot is on the ground, it's a negative 1 value. So, and we're just doing the same thing for this one, except in the opposite direction, because that's the other way. So if the value is greater than or equal to 0.5, that means it's planted on. It's basically on the ground or close to the ground. If it's less than 0.5, then that means that it's in the air, and we need to plant it. So when we lock it, we're just calling our locomotion cycles, and we're saying lock left foot. We're doing the same thing for the right one. Right here, we're just saying, is the feet position less than 0? If so, then it's the left. If it's greater than 0, it's the right. We're doing the same thing on this on the transition rules for these. In fact, we're sharing these transition rules between both the left feet. For the plant, we're blending between our third person walk at a 0.95 value. So if you bring this over until it says about 0.95, you'll see that's when the left foot is on the ground, and that's plant left foot. So we're doing a layer blend per bone. We're saying IK foot L and thigh L, just to make sure that both the IK and the thigh are both being blended towards that direction, so we don't get any funky movement, because you got to remember the IK foot bone does have an effect on the leg. So modify curve, we're just turning that on. Doing the same thing on this one, except we're using 0.45. So let's see, 0.45 right there, that's when the right foot is on the ground. And we're blending, setting the foot lock. And then we're just doing that, and that's pretty much it, guys. So that's the rundown, and I hope y'all enjoyed this. And if you have anything to say, feel free to say it. If you have any questions, feel free to ask. Any requests, anything, just let me know down in the comments. Alright.